This video is going to show an example on how to use the OTC2312 with an Arduino Uno, in specific the state-driven example. For more information about the pinouts and all the circuitry around this OTC2312, go to the Okika Devices website, download the datasheet so you can get more information. Alright, so we're going to use input header 1 and output header 1, which is connected to J input left, and the output header is connected to the jumper output left. These are single-ended connections, and then it goes through a Rauch filter that converts the single-ended to differential. The FPAA is going to compute the signal, and then it goes through another stage that converts differential to single, and then you have access to that single values on jumper output left and jumper output right. So we're going to connect a waveform generator on JIL and then an oscilloscope at JOL. I'm going to use the Analog Discovery 3 to do the whole thing, to do the waveform generator and the oscilloscope. So let's see how to set up the Analog Discovery to interface the OTC2312. So I open waveforms, I'm going to open the scope, and I'm also going to open a waveform generator, and I'm going to have 1 volt amplitude, 1 kilohertz frequency, so I'm going to press run, or actually I'm going to wait, but this is pretty much ready to go. So waveform generator, and then eventually we'll see the waveform coming out. Alright, I'm going to stop everything, and let's go back to the presentation, and let's see how to program the OTC2312. Alright, we're going to have access to the firmware code. There are 2 files that we're going to look at. The first one is the one that has the FPAA configurations, the .h, and then the second one, it's an Arduino file that has the firmware code to program or reprogram the FPAA. So let's go over that over here. Alright, so we have 2 files, the OTC Uno file and the FPAA configuration. This is a very straightforward code. Pin 10 is the one that we're going to use to do the chip select. The FPAA is interfaced by SPI. There are 2 ways to reset or to put the FPAA into configuration mode: through reset or through a software reset or a hardware reset. We're going to do software reset on this example. So if you call this function, we'll put the FPAA ready to receive configurations, and then this function is the one that is going to look at the .h file that has the FPAA configurations and sends that information over SPI. On the setup, we set up a serial port, we set the chip select to output, we initialize the SPI. We wait a little bit just to get the SPI stabilized, and then we do the software reset and we send the configuration. And then we keep idle in the loop. So if you look inside of the FPAA _ config.h, this is where we're going to put the FPAA configurations. Alright, so how are we going to do that? We're going to use Anadigm Designer for that, and you just have a bunch of different types of modules that you can use, analog modules. And this is the matching of the Anadigm Designer to the pinouts of the OTC2312. So you have access to the single-ended JIL and JIR, and then you can also access the differential. You just need to be a little bit more careful because you have the Rauch filters that can affect your signal. So this board is done to interface with the single end. And then we have also access to the single end on the output. The analog pins of the Arduino, A0, A1, A2, and A3, they're connected to the output 3 and output 4 differential of the FPAA, and digital 2 and 3 connected to the input-output of 7 of the FPAA. I'll go over on how to set up these in a minute. So let's see that example. So I'm going to bring in Anadigm, the Anadigm Designer example. So this is blank. So let's set it up. If you double click on the cells, you can set it up them as input outputs or independent amplifier. In our case, we're going to set up as an independent amplifier. We can set up additional logic around, so we can do our Rauch filters. We can do this to all the pins, and then these are just, we can set up an input, these ones as an input or output. I'm just going to use just these two. Set up this one as an output. You get the idea. In future videos we will explore all of these parameters. Alright, in my case I'm going to set up this as an input and as an amplifier filter, and I'm going to bypass the signal. Alright, the rest can be the way that it is. I'm actually going to turn them off, so it just becomes a little bit cleaner to see what's going on. Alright, I apologize for having them all on. Alright, so I'm going to save. So there are mainly three ways to send this configuration to an FPAA. One is over a serial port, but you need to have a special firmware inside of your microcontroller to receive the FPAA configuration directly from Anadigm Designer. And then you have an algorithm method and the state-driven method. So we're just going to focus on the state-driven right now. So I'm going to press state-driven. The first thing that we need to do is to select the FPAA chip. So we select the FPAA, and then we go to transitions and we select this one as the primary state. On the generation, make sure that you have generate C format configuration text files. So it's going to generate a .h file. And in this case, I'm going to generate these into the current file where I have where I save the bypass example. So I have here the file. It's empty, and I'm just going to press generate, press OK, replace, and if I open here the notepad, you're going to see that it's going to ask you to reload, and this is the information that I am going to copy to my .h under Arduino. So let me delete this, control paste. Typically I put a comment here to know what's going on over here. Alright, so now we're almost done. So let's just set up the hardware really quick over here. So let's go back to the lab bench, and you can see here that we have an Arduino, the OTC. I'm just going to connect the OTC to the Arduino. Before actually powering, let me turn off a couple of things here. Let me actually power these down. Alright, so I'm going to connect the ground. Sorry about that. So I'm going to connect the ground of waveforms, the ground of the Arduino. And then I'm going to use the waveform generator 1 into my jumper input left. The second pin here, let me see if I can zoom in. Alright, this pin is ground. It's already connected to ground, and we have things already referenced to ground, but it doesn't hurt to put another one. And then I'm going to put channel 1, looking at the output of jumper output left. Alright, I'm going to power things up, and let's go back to the software. Alright, so select your Arduino and press compile and deploy and upload, so the code gets uploaded. I am going to the waveforms, and I'm going to run the oscilloscope, and I'm going to run the waveform generator, and you can see the bypass. So if I move the frequency, so let's go and measure a couple of things under channel 1. Let's measure the maximum volt peak to peak, and let's measure the frequency. Alright, so if you see here, volt peak to peak, I'm putting 1 amplitude, so 2 volts peak to peak, and behaves properly. It's a bypass, so the signal doesn't get affected. However, if I keep cranking the frequency here, you see that now the amplitude gets reduced. So what's going on? Because Anadigm here was a bypass. Well, we have a Rauch filter, and let me go back here. If you go to the datasheet, you can see that the Rauch filter is a second order low pass filter, and it's set it up as audio in this case, so the cutoff frequency is at 23 kilohertz at -6 dB. So you're going to have half of the amplitude at that frequency. So if I go back here and I set up these around 23 kilohertz, you're going to see that I get half of the amplitude. So that's the effect of the Rauch filter, not of the code or the modules or the cams inside of the FPAA. So let's go back, put this back to 1 kilohertz. So we have 1 peak to peak. Let's give one example of a cam. So I'm going to do a right click, insert new cam, and you have a bunch of cams that you can use. I'm going to use just a gain inverter, and I'm going to reduce the amplitude by 0.5. Alright, I'm going to connect inputs and outputs. As long as I keep away from the 23 kilohertz, I'm going to see the gain affecting my signal. Alright, I'm going to save dynamic configuration, StateDriven. Everyone should be ready to just go to generation and press generate. Alright, on my notepad, I keep track of that file. You can see that it got bigger. So I'm going to copy that, go to your FPAA, .h, and I actually typically what I do, well, let me show you a quick trick. So I don't lose these, so I don't need to be generating all the time. I like to put it here, and I put a comment, and this is the comment that we have over here, bypass. So then I can just go directly there and test that if I need. I copied this one, so I go back to configuration array, put it here, and now we can just do gain inv of 0.5. Alright, cool. So I'm going to compile. Before compiling, I'm just going to have my waveform, and I'm going to set it here, and the minute that it gets compiled, hopefully you're going to see these being reduced by half. So let's just go and compile these, go into the waveforms, and here you go. You got programmed, and you can see half of the gain. So this is our gain inverter working. Alright, so I hope this was easy to follow, and more videos to come. I hope you have fun.